Good morning. Welcome to this webinar today. My name is Markus Widorski. I'm working at the Radiation Protection Group at CERN, and I have the pleasure to host this webinar that is organized by the Working Group 11 of EURADOS. So very short word about EURADOS. So the European Radiation Dosimetry Group is mainly a European scientific network focused on radiation dosimetry, so the measurement, calculation, assessment of ionizing radiation doses. And we bring together research institutes, universities, hospitals, authorities, national metrology institutes, and industry experts across Europe. So EURADOS plays an important role in connecting radiation protection research with practical implementation in different fields. And we are organized in different working groups, and among which Working Group 11 focuses on high energy radiation fields and mixed radiation fields. And in one of these tasks we are working on, we are looking at the study of dosimetry in pulsed radiation fields. And this is what our webinar today is all about. So we had a first webinar on Monday about facilities producing pulsed radiation fields. So in case you were not able to attend on Monday, you will find recording and presentations very soon on the EURADOS website, as well as of this webinar today. So today I'm very happy to welcome three speakers covering three different measurement methods in pulsed radiation fields, and they will highlight challenges and advancements in these methodologies. After the three presentations, we will have some time to answer questions that may come up during the talks. So please use the chat function at any time to post your questions so we can address them at the end. We will start our webinar today with Ariel Tarifeno-Saldivar, who is a researcher at the Particle Physics Institute at the University of Valencia in Spain. And he will speak about the REM counter development in pulsed radiation fields. So, Ariel, the floor is yours if you want to share your slides and start your presentation.
Okay, thank you very much, Marco. Can you see my screen?
Yes.
Okay, so it's a pleasure to be invited to this webinar, to talk about our project, which is called the LINREM project. This is a coordinated research and development effort by the Instituto de Física Corpuscular in Valencia, which is a mixed center between the National Research Council from Spain and the University of Valencia, and on the other side from the Technical University of Catalonia in Barcelona. So briefly, let's try to review or summarize some gaps and challenge of active ambient neutron dosimetry with this well-known instrument called REM counters. So to start, let's highlight that neutrons can dominate the total radiation dose received by workers, patients, and public. That's why after 50 or more years from the development of this kind of instrument, there is still the need for proper detection techniques of neutrons, in terms of energy sensitivity, time structure, and real-time monitoring. There are several technical fields where these kind of instruments are needed. For instance, in big science projects like CERN facilities, particle therapy facilities like hadron therapy, and of course in industrial applications. So here I summarize some of the gaps we found a few years ago when we started reviewing this technology. In particular, we found that most of the commercial systems are somehow a classical technology. The radiation sensor was developed or was conceptually designed in the 60s, while the acquisition and readout in most of the commercial devices is from the 90s or the 2000s. Then there is also some lack of portability because most of these devices, or almost all of them, are above 10 kilograms, which is an issue for survey meters, which has to be handled by hand. Okay. And then two important aspects, which is the response to high energy neutrons. Not all the devices are sensitive to newtons up over 20 MeVs. And in addition, and which is the focus of these webinars, they are not well suited for complex quasi-continuous or pulse and neutron fields. So for pulse and neutron fields, you can see the nice talk by Marco on Monday, which will be available in the webinar website. Then concerning the challenge, here I summarize few challenge we have also considered. First, the high energy neutron fields in particle therapy. Particle therapy is a therapy treatment which is evolving with a growing exponential. Yeah, so they are in particular in Spain. By 2030, there will be 13 proton therapy facilities just in Spain. So this is an important field for cancer therapy. Then, of course, in big facilities like synchrotron and cyclotron facilities, you can have beam losses, which produce sudden secondary pulse fields. Yeah. And in addition, there is also an important technology which is evolving exponentially too, growing exponentially too, is the, in particular, high intensity lasers. Yeah. So, and moreover, there are new aspects to be considered, which is basically the new recommendation for operational quantities, in particular the IQ 95 from 2020, which somehow will affect the conversion factors and the way you design these kind of detectors in the high energy region part. So concerning this challenge, you can also see the talks by Veronica, Albrecht, and Alexander from Monday. So our proposal after this gap analysis was to redesign this detector, but relying on the good, I mean, on the very robust technology, which is basically proportional neutron counters and neutron moderation. So basically, we propose two designs. The first one, which is aimed to cope with the portability issues, is the LINREM, which is a lightweight system with a sensitivity from thermal up to 10 MeVs, and a weight which is less than 4 kilograms. Yeah. So, and then for high energy facilities, we propose this design, which is the LINREM extended, yeah, with a energy sensitivity from thermal up to 10 giga electron volts and a weight less than 11 kilograms, which is still quite competitive with the commercial extended energy range systems. Overall, our designs in the version 3, you see here the number, they provide an accuracy around 10% overall from experimental benchmarks we have done. We have focused also into providing sub-millisecond time response in terms of for different neutron fields, different time structures, and for pure pulsed fields, we have a linear response up to 1 microsievert approximately. So the application for the non-extended systems are nuclear power plants, industrial applications, DD, fusion and laser-driven neutron source, small accelerator and research facilities, and of course standard radiotherapy facilities, yeah, which might produce, depending on the voltage, photoneutrons. For the extended one, the main applications is hadron therapy, also flash therapy, and large accelerator facilities, as well as air crew and space crew dosimetry. In parallel, we have also started developing or adapting these detector designs into a passive system, which is called LIMPAS. Yeah, so basically the main idea is to provide absolute ambient neutron dosimetry, which basically enables traceability of the measurements. So we have found that there are no commercial devices providing exactly the same response as an active ambient neutron dosimeter, but with passive systems. So this is why we started also to work on this. And of course, the main applications are similar for the passive system. Concerning the one of the gaps we have identified, the energy response, just let's check some intercomparison experiments. So here we compare our systems. We have performed a benchmark measurement at the SURF facility, which is the only one high energy reference facility and available in Europe, I will say. Yeah. So in this facility, there have been several campaigns, and most of I would say almost all the commercial and prototypes has been tested in this facility. So that's why we went there. And here you can see that the response of our detectors in this kind of working place is completely compatible with commercial systems. This data and this research is part of the PhD thesis of our student Benedetta Brusasco from University from Barcelona. So basically, in general, we can see that in this kind of benchmark, we can accept plus minus 20% tolerance, which somehow sets the maximum acceptable tolerance from the point of view of energy sensitivity. So this is, of course, a strong statement, but we can also consider that any deviation larger than 20% might be not due to energy response. Of course, this is for extended energy range systems. Okay. So, for instance, non-standard conditions such as pulsed radiation fields. So, what is the status of pulsed fields? In 2014, EURADOS organized an or released the conclusions from an intercomparison exercise in pulsed neutron fields. And this data is quite interesting because it shows that most of the commercial device, with the exception of looping, which has been developed to cope with pulsed fields, presents underestimation beyond 10 nanosievert per bars. So here I introduce somehow a kind of new nomenclature because we are now talking about a pulsed dose rate, which is basically the dose rate produced by a burst of radiation. Yeah. In addition, we can say that there are other technologies like activation detectors, for instance, the A-GRIM or RIM2. They don't suffer pile-up effect. They don't suffer this problem of underestimation, but they cannot provide online monitoring shot to shot because most of these devices are based on silver activation, which requires at least 2-3 minutes of counting after a single shot. One of the key conclusions is that they can also provide a correction to these nonlinear effects. Yeah, and this is one of the main focus of this paper, also to provide this correction model. Now the question is, how do we cope with the pulsed neutron field issue? So in general, most of these systems, in particular proportional neutron counters, are suited to be operated in the so-called pulse mode, which basically aims to detect single neutron events or single events in general. And for this, what we use is a proportional neutron counter, okay, which is typically helium-3 or BF3 detector, coupled to a charge-sensitive preamplifier. So here you have the standard diagram of the charge-sensitive preamplifier from the node. Yeah, and you can see that basically this system acts as an integrator because the voltage at the output is proportional to the total charge collected by the detector. And since we are operating the system in proportional mode, I mean the detector, it means that basically we can if we plot the amplitude, the spectra of the events detected, we will see something like this. Yeah, this is a standard for a helium-3 counter. This is the maximum energy deposition from the neutron capture reaction products. And here you see the so-called wall effect. Something similar is also found when you use BF3 detectors. So here the point is that since this is an integrator and also typically this detector, they have a very, very low sensitivity to gamma rays, basically they may act as an integrator when you have a burst of radiation. Yeah. So a burst of radiation looks like this in an oscilloscope. Okay. So basically, the key point in this concept was, at least, I mean, when I was doing my PhD thesis, it was proposed by a collaborator from Argentina. The idea was to count the number of detected events basically by integrating the charge and estimating in a statistical way the expected number of single events producing all this area below this waveform here. Okay, so we published several papers, including an implementation for neutron detector for fusion sources. And also in 2014, I published the counting statistical model, the way how to estimate single shot uncertainties, and so on. So basically, this is the basics of our idea of detecting pulsed neutron fields with the dosimeters, because the technology is exactly the same. And here, for instance, in this plot, you can see what happened when you pile up events, what happened with the amplitude spectra. So basically, this is for just one detected event, this is for 5 detected events, and this is for 50 detected events. So you can see that at some point, when we have a large statistic, basically this is roughly a Gaussian distribution, which is compatible with this idea. Okay. So, but of course, life is not so easy as we want. And at some point, there are some non-linear effects. And these effects appear basically because of a space charge accumulation in the proportional counter, which is basically impacting the gain of the gas inside the counter. So it leads to a non-linear response. So this effect was studied in 2014 by Rios, and they basically demonstrate that the loss of gain, which allows to enable this loss of linearity, it can be corrected by this equation, which is something very similar to the non-parallelizable model for that time effect, but the physics here is not that time effect. It's basically a problem related to the gain in the gas. Yeah, but the correction mathematically is the same. So in 2018, we started some experiments in the ENTO facility at CERN to try to study and demonstrate experimentally this kind of correction factors. And here you have some experimental measurements when you have here the two events, yeah, the two events in a pure pulsed field concerning the number of events estimated by the charge integration method. So here you have what we observe with the charge integration method, and when applying this correction, we recover linearity here. Okay, so this is the basics of our model.
You have 2 minutes left.
Oh, sorry.
It's just in time.
Yeah. So when applying this concept to our system, this is what we observe or what we get for the linear detectors. Okay. So we get roughly a linear response up to 100 microsievert per bunch. Yeah, without any correction. This is published in a paper from 2024. So here I will focus on two application examples. First one is dosimetry in laser-driven neutron source. We have used this detector for characterizing the neutron dose at the CLPU pulsed neutron source in Salamanca, Spain. So here is the setup. And they were basically discussing with the national authority the authorization of this facility to perform these experiments, and they needed to cross-check measurement with a standard system, which is the Wendy2. Okay, and we publish also this data, and what we can see here is the pulsed neutron dose, yeah, in shot by shot. And what is interesting is to see that in this kind of system, there is also that might be also a light variability. Yeah, so basically what we have done after the measurements is to recommend some values for radio protection. Then a second example is hadron therapy. So, and here the key points is that depending on the type of machine, we have different time structure. For instance, cyclotron facilities, they provide roughly a continuous beam, but synchrocyclotron, which is the new technology in most of the new kind of proton therapy centers, is providing basically a pulsed field. Yeah. So what can we do with this sub-millisecond time resolution? Basically, we can study very complex irradiation treatment plans, and we can observe with our detector the dose per spot. Yeah, so in this treatment we have 18 layers, and inside every layer we have different spots. This is the basic of pencil beam scanning, and what we see here is that by using our technology we can basically determine which is the main contribution to the total dose by layer. Yeah, and this is very interesting from the point of view of understanding or benchmarking also Monte Carlo simulation for those models. But what happened in other technologies? For instance, synchrocyclotron. This is the same this is the IBA Proteus 1 facility, and here we have the spot extractor. But here, inside every spot, what we see is a pure pulsed neutron field, a burst of radiation where we cannot see single events, and everything is pilot. And this is the main problem for this kind of facilities and standard technology. So coming to the end, what is the status and next step? So basically, the core system specification in what we aim to finally develop is an adaptive signal processing, firmware, providing sub-millisecond temporal resolution, and of course, right now with an energy response complying the ICP 74. We have additionally a conceptual detector design full compliant with the ICON 95. Of course, we have both systems in active and passive variants. The project status, we are transitioning from prototype validation to integrated everything into a standalone system, with the idea to be able to transfer this system to interested users within a time frame of less than 1 year or so. We have also ongoing experimental work at the CERN ENTO facility toward the development of a pulsed irradiation setup. And of course, we are open for collaboration and joint validation efforts. Any question is welcome. Thank you.
Thank you very much, Ariel, for this very interesting overview over the measurement and challenges and the performance in particular of the LINRAM detectors. So we go to our next speaker straight away, to Faustino Gomez Rodriguez, who is a professor at the University of Santiago de Compostela in Spain. So Faustino will speak about measurements with ionization chambers in ultra-high dose per pulse conditions. The floor is yours.
Okay, thank you, Marcus. I'm just going to share my screen. Yeah, okay. Well, hello to everyone. Thank you for this opportunity just to give the webinar. Well, I'm going to talk in general terms of the ionization chambers in those in ultra-high dose per pulse conditions, and I just put the ultra in parentheses because we will see that some of the results of ultra-high dose per pulse conditions will teach us something in the conventional pulse beams. So as you know, we in dosimetry from the standard times this last year, using ionization chambers, basically air ionization chambers to measure the dose. And our traceability is just coming from a reference field like Coral 60, and then we just measure in a different beam facility using the corresponding correction factors that are normally following recommendations for the code of practice that are published by some of the reference institutions in the field. So here I will cover essentially the electron beams because they are the most demanding, the most challenging beams in this pulsed kind of deliveries. So I will just talk on that. I mean, well, in the 2019, more or less, we just were challenged to review the ionization chamber dosimetry and ultra-high dose pulse conditions in electron beams. And what we saw immediately when you put the ionization chamber, a commercial ionization chamber in this kind of beams, and you get to dose per pulse of 1, 2, or more grays per pulse in a few microseconds, which is what this kind of deliveries can produce. This means that the instantaneous dose rate is of several megagrays per second. You have large losses of charge during just produced by recombination in this kind of chambers. And this graph is from the Peterson paper on the advanced Marcus, which is a chamber with 1 millimeter gap. Okay, normally what we are saying when we have this kind of losses is just try to calculate the charge collection efficiency or the saturation factor, which is the inverse of that. And then we have the, let's say, evaluation of the dose produced by the chamber, just compare with the dose that we have from some reference instrument. And you can see they have all these correction factors from the beam quality, the polarity effect, the pressure and temperature effect, and then they have the chamber readout, okay? So originally in the 60s, Boak produced this theory that describes the recombination. But when we compare with the actual experimental results from many chambers, and here in the plot there are parallel plate chambers, the line coming from Boak theory is clearly out of the experimental data. Boak has always produced in this original theory a correction factor that overestimates the correction. So people knew that at the beginning of this history, and then several approaches just to try to deal with that kind of situations. The first one just was to produce kind of phenomenological description of the saturation effect. And this is the logistic model that I have here, where I have written it in the terms of the U parameter, which is this non-dimensional parameter from the Boak theory. And then if you use the logistic model, you have this black line here that more or less reproduces the shape of this recombination behavior. Okay. Boak in the 96, in the past century, he knew that there was something lost in his theory, because he was just supposing in the original theory that there were only ions in the chamber. But there are free electrons, and even for a 2 millimeter chamber, we have like 40% free electron fraction. And the free electron fraction is the yield of the part of the electrons just released in the chamber that are able to reach the positive electrode. So he modified his theory just to include this free electron fraction, which is here written as a P. And this free electron fraction, as you can see, depends on this delta parameter, which is basically proportional to gamma, which is the attachment rate to oxygen mainly, and then a geometrical factor G, which is normally D to the square, the gap between the electrodes for a parallel plate chamber, the mobility of the electrons in the denominator, and the voltage of the chamber. Okay, but whenever we compare these modified theories to experimental values, we can see that none of them reproduce the experimental data. The logistic is still able to have some shape that is close to the experimental data. So we knew that the theory was wrong. So the theory, in fact, if you only take 2 ions in the chamber and the free electrons, is something like this, where you have a transport of carriers that is coming from the ionization produced. This is the term that produces positive and electrons, positive ions and electrons. We have the ion-ion recombination, electron-ion recombination, and we have the attachment, which is this gamma term here. Okay, so afterwards, Fenwick and Kumar, they were able to solve analytically the problem with the 3 carriers with this new theory, with this new formal theory that you have is a modification of the Boak theory with this H function that depends on the delta, which is just parameterizing the attachment, and this E1, which is the exponential integral function. Okay, so unfortunately, just to solve it analytically, you need to suppose that there's no screening effect in the electric field and the delivery is instantaneous. And this is because to solve the problem with the screening of the electric field is highly nonlinear, and then you cannot solve it by standard mathematics. So one of the 2 outcomes from this situation in which we have 3 carriers and we have 3 electrons is that in the original Boak theory, we were just supposing that if we expand these terms of a logarithm of u divided by u, then we have that the inverse of the charge is proportional to the inverse of the saturation charge. And then here you have u, but this u is inverse to the voltage. So if you plot the inverse of the charge respect to the inverse of the voltage, we expect a linear behavior. And the extrapolation will give the inverse of the saturation charge. But this is what we call the Jaffe diagrams, just to evaluate the combination in ionization chambers. But if you take the Kuma-Fenwick solution, this is not true. And why? When we go to a low gap chambers, this inverse of the charge respect to inverse of voltage is nonlinear. And this is not because any multiplication, is because there are free electrons. If you increase the gap, then it tends to be linear. So this kind of Jaffe diagrams is a kind of limit behavior of chambers, but it's not accurate again. So if you go to experimental data, this is the data that is published from PPT 05. You can see the non-linearity when we go to high voltages in the Jaffe diagram, which is really agreeing with the simulations and the expectations from the analytical solutions. So what is the reality is that when we have all these things in the chamber, we have ions, positive and negative, we pass electrons, and we have a screen of the electric field. So we have all these equations in which have recombination in the two different forms, ion-ion and electron-ion. We have diffusion, we have multiplication, and we have attachment. So it is possible to solve these kind of equations, but only numerically. We cannot solve it analytically if we take all the physical processes inside of these equations. But you can have the solutions now in GitHub in these two places where you can have the solutions for parallel plate chambers and also for thimble chambers using finite differences or finite elements. So now we have really a way of elaborating this kind of recombination models. It is important, the electric field, because if you just suppress electric field effect in this evaluation of the behavior of a chamber, you can see how much the charge collection efficiency is varying. This is for advanced Markov chamber, and this is for those propulsed over 1 gray. On the other side, electron-ion recombination, what we can call direct recombination, is not so important. And for a standard air ionization chamber, is normally below 1%. So you can see that ion-ion recombination is the big part of the problem. If you look on the actual solutions of this problem using the most accurate simulation that we have, then you have this kind of perturbation of electric field. This is a parallel plate chamber with 1 millimeter between the electrodes. The nominal electric field is this red line. And when we switch on the beam, this is a pulse of 4 microseconds duration and 5 gray per pulse. You can see that the electric field is highly perturbed. And we have this kind of linear slope close to the negative electrode where the positive ions are collected, because there is a balance of charge where we have a large amount of positive net charge close to this electrode. And this is producing this slope here because of the Poisson equation. On the other hand, we can also resolve the instantaneous current of the chamber, and we can see the pulse here, this 4 microseconds. We have the electron current and the ion current, and we can compare with the actual data. That's something that we did. And this is the results for a frost chamber. In here, you define the different free electron fraction. This is the Boag original free electron fraction. And people confuse this free electron fraction with the fraction of the signal that is due to electrons. Because the signal in any ionization detector is produced by induction. Really, if all the electrons were collected, they will produce only half of the signal. The other half is going to be produced by ions. So the induction free electron signal is 0.5 in the limit. And what we can measure is the fraction of the signal produced by the electron drift divided by the actual charge that we have, what we call the effective free electron fraction. And we just measure that in the MELAF at PTV. This is a 20 MeV electron beam with a pulse of 2.5 microseconds. This is instantaneous current solved. And this is the effective free electron fraction compared with the actual data. So you can see it fits. On the other hand, we can really compare electron simulated current contribution, the positive and negative ion, and compare with data. and the integrated charge. And this gives us a benchmark of simulations, and let's say it gives us confidence that we understand the basic processes that are producing this kind of problem of recombination in the chambers, okay? So not only we can reproduce the instantaneous current, we can reproduce the free electron fraction, but also we can reproduce the saturation effect, the charge collection efficiency, and this is the case of the Roche chamber again for different voltages and for different polarizations. It is important to understand that if you just not have the correct parameters in this solution, for example, you miss a correct electron mobility, you will not get the right instantaneous current in your result. So it is quite demanding from the point of view of reproducing the actual data, okay? Next step was that we realized the importance of the electron distance in the recombination. And this is a paper of Raphael Kranze. They produced different chambers with different gaps. And when we go from 1 millimeter down to 0.25 millimeter, you can see that we have large recombination effects. But in this 0.25 millimeter chamber at 500 volts, then there's nothing, almost nothing. So we are just being able to collect all the charge that is released in this volume. And then we have somehow solved or just minimized the effect of recombination. Well, this was, it was called the ultra-thin ionization chamber. The first prototype was produced in my group in Spain. And afterwards, it has been going to all people in different places. Now, there are one commercial chamber is 0.3 millimeter from the standard imaging, the A30. And there are several prototypes from different companies that are still not commercial, but probably they will be. So you can see here the comparison of the dose per pulse reading on this kind of chambers for chambers of different gaps. And you can see when we reduce the gap, then the simulation, which is the continuous line, and the data agree very well. And then this chamber has a very small recombination effect up to 6 gray per pulse, which is less than 1%. So there are two problems when you go to this kind of limits in the design of chambers, and it comes from physics. So the first one is that if you increase the electric field when you produce the so small gap in the chamber, then you are being closer and closer to produce multiplication by electron collisions in the gas. So this is the first 1000 coefficient. And if we operate the chamber at high voltages, we can see that there is multiplication in this curve. You see this increase of the signal here is coming from multiplication in air. Okay, so when we first measured that in our lab, we were just hesitating if this is possible to have multiplication in air, but of course it is. I mean, you can have that. On the other hand, because of the symmetry, we will better not trigger this kind of multiplication. Normally, we just keep for this kind of chamber in a region where the multiplication is negligible, if possible. On the other hand, we also we also have the prediction from the theory that it will depend this recombination on the density of air, and it was pretty confirmed by PTB after work on experimental data of 2 years. And you can see here the different recombination that diminishes with the absolute pressure. And the recombination scaling is here coming in the dose per pulse squared to the pressure, which is something that probably is surprising for someone, but we can predict the charge collection efficiency when you change the pressure through this kind of scaling. Okay, other approach has been just to use low pressure, just following this idea. And this has been done by the Pisa University group in the what is called the all ionization chamber. Here you see a nitrogen-filled chamber, and then you can see here that it could measure up to, let's say, 8 gray per pulse, working at 50 hectopascal and with a voltage of 150 volts. And this is something which is still under development, but it seems to be one of the possible approaches to this kind of high dose per pulse, okay? For the general idea of how to deal with that, with the standard chambers, there were some people thinking, okay, maybe we have a large recombination, but maybe we can characterize that recombination for each model of chamber and correct them. And this general correction factor will be distributed for anyone, and then we can still use chambers. But in a work that was done by Alexander Borgin and many other people from PTV and other institutions, we saw that the intramodal variations of the commercial chambers and the high dose per pulse is very large. Let's say 8% for the PPC05, 16% for advanced Marcus. And this means that using a generic correction factor will introduce large uncertainties and is not very recommended. Okay, so these are the three things of this large variation of TCE. We would say that this large uncertainty, when we calculate the KSAT, gives us a problem when the KSAT is very large. We do not recommend to have correction more than 5%. And we also, even after correction for KPT, we have dependence on the pressure. So we know about all this. The problem is nonlinear and so on, but there are some invariances in the solution of the saturation of the chambers. Like, for example, we know that the TCE is invariant when you use two different chambers and two different voltages. Is the square of the distance between electrodes to the voltage is constant. And we also know that even when we have a large nonlinearity and the electric field is perturbed, the collection time for the ions is inverse to the voltage, even for high dose per pulse. I mean, this is quite curious, okay? Yes, following all that, we also made the work on the thimble ionization chambers, and this is the result. We are able to reproduce again this result for the pinpoint chamber. But one thing that is very interesting is that the recombination in the thimble ionization chambers is polarity dependent. So it's different when you use the polarity of positive charge collected in the collecting electrode, or you collect negative charge there. And this is something different because it makes up what is normally used for correction. It makes up the polarity effect and the recombination of saturation correction factor. This is something that we're using time-resolved instantaneous currents. We can see in here when you have you are getting negative charge in the central electrode, you have more negative charge than when you are collecting positive charge in the central electrode. Okay, so just taking all of this and you're going back to recombination, and this is affecting everything when we are in pulse beams. The old theory of Boak was predicting that the behavior when you have the two voltage method, for example, you measure two voltages and you have the ratio of the charges, you have this kind of expression in the code of practice. These coefficients do depend only in the voltage ratio. So it's the same if you have 200 and 100 or 300 and 150, but we know that this is not true. When we just compute, we take data of different combination of voltages and the ratio is always the same. You have different branches in the experimental data. So Boak theory is wrong. And what we have in the actual problem is that these coefficients depend on the pair of voltages you have chosen. They depend on geometry and they depend on the pulse duration. And this can only be solved using numerical methods, okay? So just going back to summarize of this, and this is going to be presented at Estro. Here there are a lot of chambers. Here there are parallel chambers, there are cylindrical chambers, and in here you have in the gray, this is the result of the chamber deviation when you don't correct for anything. The blue ones are when you correct by the numerical model, and the let's say pink ones is when you correct according to the two voltage method that is in the TRS. So if you look at that plot, you can easily understand that our method for correction of saturation is not the right one. And even for some of the chambers, especially for the low gap chambers, to correct is worse than not correcting anything, okay? So this is why we think that we have to review all that subject of recombination in the actual dosimetry in pulse beams. Because if you, for example, look here, there are two chambers here. It's the Farmer and the advanced Marcus, okay? So in the Farmer chamber, the dose per pulse is small. And because of that, the electric field is not perturbed. So the Fenwick model is just coinciding with the numerical model and the data. The Boak, of course, is out of the market. It's too large, the correction. But if we go to the advanced Marcus, dose per pulse is large. I mean, the Fenwick model is just departing from the actual data because of the electric field perturbation, and numerical models are able to reproduce actual data properly. So as conclusions, The implementation of this ultra-high dose rate and ultra-high dose pre-pulse just put some significant challenges on the dosimetry using the gold standard. This is ionization chambers. We would not say that it is very reasonable to use generic corrections for that, and even using a correction factor bigger than 5% is discouraged. I mean, we would say not to use that. We have one of the solutions used to do the dosimetry with the smallest electrode spacing chambers, like the ultra thin chambers, and we have found that all this review of the standard recombination theory shown that a standard box theory and the standard methods which are in the code of practice has to be really re-examined, and probably we have to think of a new formalism of doing that more accurately at the moment. Okay, thank you very much.
Thank you very much, Faustino, for presenting this very, very relevant research topic, in particular in view of upcoming flash therapy applications, I guess. So we go to our last speaker today, who is Benoit Lefebvre. He is working as a detector scientist at the Eli Beamlines facility in Prague, and Benoit will report about his work on filter stack spectrometers. Benoit.
Thank you. Thank you for the introduction, Marcus, and for the opportunity of presenting my work at in this webinar. I would present a practical guide on how to implement this strategy of using filter stacked spectrometry for pulsed radiation field, and an overview of our experiment at the Eli Beamline using this type of detector. We so the we know that there are intense pulse radiation field produced at laser facility and in other fields, scientific, medical, and industrial. This I don't need to convince you of that anymore. But from the point of view of a laser facility, it is very important to do the characterization and spectrometry of these fields, which could be to probe the physics processes at the source, for example, at the laser target, to get feedback from the beamline for the tuning operation, to do ambient dosimetry, and and shielding assessment. But it can be impossible to achieve precise spectrometry. It could be because you have simply too many particles at once, so your spectrometer saturate. For example, if you use a pixel detector, you will have too many particles within one cell, or too many within the time window of your spectrometer. So one possible approach, which came up like in the last 10 years or so, is to do filter stack spectrometry. What is it exactly? So you will use those sensitive layers which are interlaced with radiation filters. So for those measurements, you could be using anything, image plate, TLD, OSL, so any dosimeter. But if you will do a high rate measurements, which is anything more than like, once every minute, every few minutes, then you will be using scintillators, silicon sensors, and so on. So the concept is we will get information about the radiation field, about its spectrum from the longitudinal dose deposition. So you will measure. For example, here you have an example with a scintillation stack. So this one in particular, it has no filters because except maybe for two pieces of lead at the end. So you measure the dose with the camera. So from the light produced by the scintillator, you get those measurements. So you will get you measure the shape of the dose deposition along the stack. And here another example with the image plates. So you will measure the dose in each of these image plates, and then you apply an unfolding algorithms, and then from this you get the parameters of the field. The unfolding. There are two main approaches, but which are actually equivalent, but let's say two ways to think about it. So either you would return a direct energy spectrum, which can be photon or electrons, but then with limited degrees of freedom. And something to keep in mind is that this technique is not magic. It will not recover a precise spectrum like if you were doing like a standard spectrometry, or you can return like just a few parameters of the field. But for both of these approaches, you need to determine the detector's response matrix, which follows from this formula. So, for example, so you will have this. This is a matrix RM, which you multiply to your the true spectrum, and then this will give you the dose measurement. So a vector of dose, which is the dose in each of your dose measuring cells, units, or tile, whatever you call it. But the unfolding is not a trivial matter at all, because you might think that you can trivially invert the response matrix, multiply by your dose measurement, and then it returns the spectrum. But in almost every single case, it's not possible to do that. This matrix is ill-defined. And also you get into other issues like degeneracies and so on, which I will talk about later. I will give a first example of such detector that we developed at Eli Beamline, which was used at LMIA, at the LMIA Beamline, which is our ion acceleration platform, driven by a 1 petawatt laser, which can accelerate protons up to 30 MeV until now. So it accelerates proton through the target normal sheet acceleration mechanism, and through this mechanism there are copious amounts of photons which are produced from the laser target. So when the laser impinges in the target foils, you get lots of electrons which are ejected, and then the Bremsstrahlung photons.
I believe we have lost Benoit. Francesco, can you?
Yes, but I don't know what's happening. Maybe it's a problem from his side.
Okay, I can still hear you and see you, so maybe we try if you can rejoin.
Can we tell him to disconnect and reconnect, maybe?
Maybe yes.
Sorry for that to everyone.
So while we're waiting for Benoit, if you have questions, please post them to the chat so we can, Faustino and Ariel already answered them there. We might be running a bit late, so we will not have a lot of time at the end to answer questions. So anything that can be answered, I am sure that the speakers will be happy to receive your emails in order to reply to your questions or to get into further discussions maybe on the topic.
There is already a question by Harald Dombrowski, but it was already answered by Ariel. Maybe Harald, please feedback if the answer is enough for you.
You cannot see, Benoit has not reconnected yet.
Maybe he's not aware.
But if you have removed him, probably, don't know. I'll get in contact with him.
Yes, thank you. Sorry to everyone, but these things do happen when we have online webinars.
Not sure. if you will see my message.
Marcus, do you have his phone number, maybe?
No, this I have sent him 2 messages on different channels where I could reach him usually, but I can't get him here. Okay, what I suggest while we are looking forward, maybe he's connecting again. If there are questions now already, then maybe we can go to the question and answer session, and we'll see when Benoit comes back if he wants to finish his talk or can finish his talk. So I can see no question in the chat. If someone wants to ask a question, you can unmute yourself as well as ask a question.
Okay, Marcus,
Yes.
Benoit is trying to reconnect.
Okay, thank you, Veronica.
I'm on the phone
people
with
from
him,
Prague are
but,
connected, so
he's not at Eli.
he's not a leader at the moment.
Or maybe something I could do is
Yeah.
also connect to Zoom over the phone, maybe.
Okay, maybe you can try this, yeah.
But I have some difficulty in possible now.
It should be. I never had any issues with this.
Because it looks like at least over the phone we have a good
Yes, please do try.
we have a good connection.
Yeah.
So
Please do try.
yeah.
Benoit will try to connect through his handy.
Okay.
But maybe Marcus can share your slides for you. Maybe
Yeah,
I can slide. Yeah.
So Marcus, if you could please share the slides from the backup
Sure.
for Benoit.
Yes, I have them open. He just has to tell me from which slides he.
Thank you very much.
Thank you.
The pool itself, and that's, I think, quite much better.
Veronica, you're still in contact with Benoit? Okay, let's see. So back maybe to question and answers if Benoit is not able to join. So there's a question from Antonella. Thank you for the speakers of both webinars. As there's no primary calibration facility available, what do you think would be essential requirements for building one today? So that might be even a question maybe for Marco Carazana, who could answer that.
Oh, can you hear me?
Oh, Benoit, you're back?
Yeah, I'm back. I'm over the phone now.
Okay, we can hear you. Can you see the slides where you are?
Not at all, because I cannot see the slide. But if you tell me on what slide we are, because I think you are showing them now.
Yes. So we're on slide 3, if I'm not mistaken.
You lost me on slide 3.
Unless someone is correcting me, yes. Ah, no, we were
Okay,
no, we're further down. We were after response matrix, yeah. So slide 6.
Okay. So on slide 6. Okay. So response matrix for this. Okay. Okay. So very sorry about this. Somehow internet connection was very good until now. So I will try to finish this quickly. Yeah, so I was showing you like this EMI beamline. So there you see the model on slide 6. So we have 2 filter stack spectrometers, and we did a precise simulation of this detector, simulating different temperatures like that. On the bottom right, you see the response matrix that we obtain for the detector. And then the idea is, if you go on slide 7, is that we will unfold, try to guess what are the number of photons N1 and N2 with the temperature T1, T2 using a least square minimization. And then we measure a response similar to the plot you see on the left. And then the fit like found like from this measurement what is T high and T low like this. So we get temperatures of the order of a few MeV, which we follow shot by shot, and then some amplitudes, which will be in units of photons per unit of solid angle, like that. So for that to work well, to get an actual number of photons, you need to do a calibration of the detectors on slide 8. I show some details of that. So you can so one approach we use is to irradiate the detector with ISO photons at 0, which is a metrology facility in Prague. Or you can in-house, we can achieve a calibration with the radiation source, or again with a strong radionuclide, also in a metrology facility. So the goal of that calibration is to get the absolute photon count at the source. It can be to equalize the channel response, but most importantly to validate your simulation model to make sure that your assumption of the materials, physics model, and so on are right. Ideally, this calibration should be done with a precise post-radiation source, but this is rarely available for calibration unless your institute is set up for this. But as it is, you do it with steady radiation sources. There's a few systematic effects you need to take into account. Now I am on. I will move to slide 9. The first notable one would be the point of view effects, which happen when you have a very large stack, which is imaged with a camera. So we have set up a test bench to estimate this effect. So there you see a camera with some scintillators in a dark box, and if we move the scintillator around, like along the z-axis, we see that the light output by the scintillator, like the light intensity decreases, and this the effect can be estimated from first principle to estimate what it could be, and then to correct it eventually. But ideally, you will need to design a detector which has a light sensor directly coupled to your light source, to your scintillator or light guide. But sometime in practice, it's not always practical to achieve this. It's not always the easiest solution. Then on slide 10, another very important effect is the ambient radiation source. So I show you an example of one spectrometer we developed for our gammatron beamline, in which you see that you have a gammatron X-rays, like the red arrow, which go forward, but they are generated at the laser target from electrons which wiggle in the target plasma, and these electrons are deflected along the blue arrow that you see there. They will go straight into a dump. So here you see the FLUCA simulation showing fluences of photons. And then if you put the detector to position, so let's say pos 1 and pos 2, you see that in position 1 we get a pretty strong signal. But in fact, most of that signal is the background, which comes from electrons backscattering on the dump. And on top of that, the camera picture is quite noisy. We have lots of grain into it, and both these effects are spoiling the signal. So then, but then if you position the stack behind the dump, then you get a much cleaner signal. But even then, this was not quite enough. Because ideally, like both the camera and the stack need to be very well shielded, like all around, so that the signal is really as clean as to get a more precise unfolding. So this is one thing. The other thing is, if you use scintillators, you might want to simulate the light to at least understand light propagation inside the scintillator, light guides, fibers. Account for spills between channel. You might have effects of Birk's saturation quenching in the scintillators. Another important thing is that so far I talk of like radiation field in a generic way, but this technique is mostly applicable to photon fields or electrons. I didn't mention neutrons. As far as I know, the technique cannot be used was not successfully used for neutron spectrometry, which means that they would consist of a background for the technique. I mean, they need to be their effect need to be considered in your analysis, and so their effect could be estimated from a simulation, for example. I think I will skip slide 11 because yeah, we skipped slide 11 because of time, and also there were some animations. I think it will not be it doesn't make sense. We can go straight to slide let's say 13. Let's say. Yeah, I will. Okay, so now I am on slide 13, and I show you an example of a TLD-based photon spectrometer from people from PTB. Here I need to be careful what I'm talking about because there are two others which are connected to this seminar. So this is it uses a few passive dosimeter with 20 metal filters of increasing Z values, and then they try to reconstruct a photon spectrum divided in 60 energy channels. And they use some model of the spectrum which is based on empiric, which is their best guess which has energy rise. So let's say between 0 and E rise, they assume no photons at all. And then they guess that there will be some peaks in the spectrum, and then that eventually the spectrum will have will fall off at some energy end, E end. Then based on the dose measurements in each of the TLDs, they apply a Bayesian unfolding, which reconstruct the spectrum, and then the unfolding starts with some star spectrum, which is the gray line in the plot, and then for using two different configurations, then they will unfold. They manage to unfold two different spectra for the set for these two series of measurements. And then from the spectrum, finally, you can, using the proper IC, you coefficients. You can calculate the H star 10, the R Kerman, and so on, other operational quantities, for example. Then on slide 14, just want to mention that we attempted to measure also protons using this technique. Here we used a smaller dark box with some small stack with plastic scintillators, so 1 centimeter long. But then for this one, we also performed simulations as a function of the proton energy, but also one of the free parameters of the fit was the quenching, so the Burke's parameter. And then we kept them as free parameters of the fit to reconstruct the response that we measured from the camera, as you see on the right. And we are currently using this kind of a stack at Elimaya for the protons that are measured there to measure their energy. Then we'll finish with some comment on other possible unfolding algorithms. Starting on slide 15. So the researchers at Eli Beamline developed a technique based on the genetic algorithm to perform unfolding. So the first step of that technique is you define a cost function, which could be, for example, the sum of squares of the difference with the best of the response given by the unfolding to the measured response. For example, a bit like a chi-square minimization. But the difference is that you need to not only calculate the cost function, but also generate a generation of spectra. And then each member of the generation, each spectrum of the generation will have a cost function, and then you select only those which have the smallest value of the cost function. And then you will move on with another generation, which will randomly generate new spectra, and then again calculate the cost function, select the best one, and then move on until you reach a satisfying convergence. So this is an interesting technique in the sense that it can recover some unexpected features of the spectrum, but you have to be very careful with that because it can become too imaginative. Let's say if you have larger errors in your dose measurements. Again, this technique is not magic. Based on you don't have a very large number of dose measurements, so necessarily the spectrum that you would recover cannot be very detailed, even if your algorithm will claim to be. So now on slide 16, so in the last couple of years, there were lots of efforts into improving the unfolding techniques, which could be to optimize the design of the spectrometer, like in the first in one paper I show here from Wen in 2023, where they used the unfolding algorithm, but this time not for unfolding, but to optimize the design of the stack. 2 years ago, there was an attempt to use a perturbative minimization algorithm, which is very similar to the genetic algorithm, but with a more gradual convergence. So it attempts to perturb different parts of the spectrum and then see whether or not you get a better fit from that, and if not, then you move on and try different parts. And again, this is an attempt to find unexpected features of the spectrum. And then there were some attempts like using artificial intelligence, so let's say a neural network to do the unfolding. And with this, you get a much faster convergence. But then this technique, contrary to, let's say, a Bayesian unfolding or chi-square, it doesn't report the error, like for example, confidence intervals. So it's very difficult to get an idea of how accurate it is. Let's say it's a bit more tricky. So I will conclude on slide 17 to say that in the last decade, so various implementations of filter stack spectrometers were developed, but that we are still trying to figure out how to best achieve the unfolding and also the detector construction. That the technique is not perfect. There can be, we still have problems with the degeneracies and problems with the relative minimals in the minimization. But nevertheless, while the information it provides is limited, it provides valuable spectral information which will not be possible to recover otherwise. And we're likely to use the technique more and more as as we encounter more post-radiation field. But they will need to be get an even better readout rate accuracy, and we need to broaden the range of applicabilities, for example, to neutrons, and so on. So I think the technique has a bright future, and we're barely starting to efficiently use it. Let's say. So thank you very much.
Thank you very much, Benoit, as well for recovering the technical issues we had. Thank you very much for this overview on the spectrometer technology. So if there are questions, that would be the last moment. We're a bit late. We are 50 minutes late. Thank you, everyone, that stayed with us so long.
But Marcus, we have to answer the question from Antonella.
Yes. So I don't know, Marco Carazana, if you would be ready to give a short response to the question from Antonella.
I'll be glad, but can you repeat the? Okay, sorry. Let me check the
chat. The question is, what would be a facility like?
Okay. Well, actually, yes, that's a big problem that there are not calibration facility for mixed and pulse radiation. It's good, Antonella, that said mixed pulse radiation field, because the capability of distinguish a situation in which you have a pulse neutron field overlapped to a steady mixed field is probably the most challenging situation, especially if this mixture of the two components is varying. This is typical along linear accelerator. At the beginning, typically you have an intense gamma field, but when in a low neutron field. But at the end of the acceleration path, probably the situation is completely reversed. I don't know exactly where such facility could be done. What is important is to have the possibility in this facility of varying the repetition rate and varying the duration of the burst. These are the two key points, and the intensity of the tricky point, the intensity of the burst, of course, because the goal is to identify or to demonstrate what is the linearity. The key information to the final user is up to what kind of dose per burst I can use my instrument. This is the key point. It is less important the energy distribution of the neutron field. This is probably less affecting the instrument response. Should be known, of course, but there is no particular constraint on a specific distribution. So can be also neutron below 20 MeV, which is, the division line in between high energy neutrons and low energy neutrons.
Many thanks, Marco, for taking this over. Given that we are 20 minutes above our scheduled time, what I would suggest is that we close the webinar at this point, as there are no longer and further questions. I highly encourage you to reach out to our speakers today. So you will have the slides available online, so you'll get their contacts as well. So if there are intriguing questions that have been triggered during the presentation, so please reach out to them and get in contact, and hopefully you can get some useful answers for your applications or your questions you have. Many thanks as well to the support team today from EURADOS, so Kerstin, Francesco, Anna, and Agnieszka, who is not online, but for the support today, making this possible. Of course, to all the speakers for their preparation and contribution, and for all of you that remained even until now with us attending this webinar, and hopefully seeing you next time for a next webinar from EURADOS. Thank you very much.